So today I wanted to talk just a little bit about mass spectrometry. And basically, what happens there is there's a cathode ray tube. And what's going on there, and it was invented by J.J. Thomson, basically, or it wasn't invented, but it was used by him to discover the electron. And it's using the same principle that he used, where you have um, basically a particle is emitted here and it's running through here, and it runs through this field where there's a plus charge on this side and a minus charge on this side, and you're basically shooting negatively charged particles. And since negative is attracted to positive, the positive here causes the particle to curl towards the positive. Now, there's two things that will make it curl more. One, if it has a greater charge, it will have a stronger attraction and curve more. Second, if it has less mass, there's less mass to, kind of for the inertia to continue forward, and it will curl more. So the smaller the mass or the greater the charge, it will curve more. The greater the mass or the less the charge of the ion, it curves less. And essentially what a cathode ray tube will do then in mass spectrometry is to cause particles to bend based on their mass. And as a result, you can then sort particles by size and then get a feel for how many particles of each size there are. So for example, this would be a situation where it's shooting particles here. The particles wrap around and come to the detecting place, and you can actually separate out particles that might be 44, 45, or 46 atomic mass units in size. So you can actually sort them out and see how big they are. And again, it's that ratio of mass over z as the charge. And so this is a picture of what it might look like for CO2. And you'll see that there's a series of lines that correspond to particles of various size, which means that for CO2, most of the particles would be of this size at like 44, and then you'd have lesser amounts here, there, and there. Now each compound or each substance will have a different signature of what's shown here. So here CO2 is a mass of 44. And then there's fragments. So just CO plus is 28. O is 16. And just carbon is 12. So essentially the mass spectrometer has separated out the fragments of CO2, the carbon, the oxygen, carbon and oxygen together, and then CO2 plus there, which is where most of it would be. If we looked at bromine, bromine is actually made up of two different isotopes. About half of bromine has a mass of 79. About half of bromine has a mass of 81. So what we see is, again, fragments where it's broken up into the 79 and the 81 isotope, just single atoms. And then we have here where it's still two atoms and it's just lost an electron, or lost an electron to get the charge there. And so you end up having about a quarter of them have basically both of them being bromine 79. Then a quarter of them have both 181, or sorry, 81. And then half of the bromine will be made of 179 and 181. So again, you can see this would be the signature for Br2, or bromine gas. Now, this can be used then in terms of making, basically looking to see if something like illegal steroids have been used. So if you were to just run a normal urine sample, you're going to get a series of peaks. Now, when you use steroids or drugs or something like that, the body will be breaking those down, but then again, there will be a signature of the particles that are left from the breakdown products of the steroids that are produced. So then if an athlete were to have urine that has both the normal peaks and peaks that correspond to what's seen in um, in that steroid, that would indicate that the athlete had been using this steroid, and it shows up there. So mass spectrometry is used extensively when testing athletes for, or in any case, for testing for use of illicit drugs or steroids.